You already know how to find the area under a curve. But how do you find the volume of a 3D solid, a vase, a dome, a cone? The trick is beautiful. Take a flat region, spin it around an axis, and add up the slices. There are three methods: disc, washer, and shell, and they're all the same idea: slice, spin, integrate. Let's watch a flat drawing turn into a solid and the formula write itself. This is full marks. Today, volumes of revolution, discs, washers, and shells, and then 2 exam-style problems solved start to finish. Start with the disc method. Take the region under a curve and slice it into thin vertical rectangles, each of width dx. Now spin one rectangle around the x-axis. It sweeps out a thin disc, a coin, whose radius is the height of the function and whose thickness is dx. The volume of that coin is pi times radius squared times thickness, pi times f of x squared dx. Add up every disk from A to B and the sum becomes an integral. The volume is pi times the integral of f of x squared dx. Now the washer method. What if the region doesn't touch the axis, there's a gap or a second curve below? Spin it and each slice is no longer a solid coin. It's a washer, a disk with a hole punched through the middle. So you subtract the hole. The volume is pi times the integral of the outer radius squared minus the inner radius squared. Big radius r reaches the far curve, little radius r reaches the near one, both measured from the axis of rotation. There's a third way, the shell method. Instead of slicing across the axis, slice parallel to it and spin. Each rectangle sweeps out a thin cylindrical shell like a tin can with no top and no bottom. Here's the trick: unroll that shell flat. It becomes a thin sheet. Its width is the circumference, 2 pi times the radius, its height is the curve, its thickness is dx. So the volume is 2 pi times the integral of radius times height, dx. Disc, washer, shell, it's the same move every time. Take a slice, spin it, and integrate. You just pick whichever method makes the radius and the height easiest to write down. Exercise 1, exam-style practice. Take the region between y equals x and y equals x squared and revolve it about the line y equals 1. The two curves meet at 0 and at 1. Because we're revolving about a line above the region, each slice is a washer. Measure the radii from y equals 1. The far boundary is x squared, so the outer radius is 1 minus x squared. The near boundary is x, so the inner radius is 1 minus x. The volume is pi times the integral from 0 to 1 of the outer squared minus the inner squared. Expand the brackets and the inside simplifies to x to the fourth minus 3x squared plus 2x. Its integral from 0 to 1 is 1/5. So the volume is pi over 5. Clean and exact. Exercise 2, the shell method. Take the region between y equals 2x and y equals x squared from 0 to 2 and revolve it about the y-axis. Vertical slices run parallel to the axis so they become shells. Each shell has radius x and height 2x minus x squared, the gap between the curves. The volume is 2 pi times the integral from 0 to 2 of x times that height, that's 2x squared minus x cubed. Integrate 2 pi times the quantity 16/3 minus 4, which is 2 pi times 4/3, so 8 pi over 3. A different method, the same clean idea. Recap: to find a volume of revolution, slice the region, spin a slice, and integrate. A disk is pi r squared dx. A washer subtracts the whole, pi times big R squared minus little r squared. A shell is 2 pi times radius times height dx. Measure every radius from the axis and pick the method that keeps things simple. We've now handled curves, areas, and volumes. Next, things start to move. A particle traces a path with velocity vectors pulling it along. Parametric curves and motion next on full marks.